You've been in thermo class now for a few weeks, and you're starting to think, gosh, there sure are a lot of formulas in this class. Man, how in the world can I keep all these formulas straight? And probably you've been in class long enough to where you're starting to have homework or problems in class that might be closed systems, and some are open systems. You're having to make some decisions. What I'd like to do is talk to you a little bit about keeping the first law of thermodynamics straight in your head, so that you don't have to worry quite so much about all these formulas. So let's get started and see if I can help give you some ideas on how to reduce your mental load on keeping all these formulas straight. Okay, so I've entitled this a crash course on the first law. And the reason is that this video is not deriving the first law of thermodynamics. It's depending on you knowing that, well, the first law of thermodynamics could also be called an energy balance. And the trick as a student and as a practicing engineer is to understand the power of the first law and how to solve thermal fluids, heat transfer problems utilizing the basic fundamentals of the first law of thermodynamics. So I call it a crash course. Um, I'm trying to throw in some of my tricks of the trade that I use throughout my engineering work, engineering practice, and also recognize that I'm trying to give you some ideas on going. Of course, we're going to start with the fundamentals that are presented in your textbook, but I'm going to give you some opinions about how might you be able to keep these things straight in your head to try to simplify your life and improve your problem solving skills. Okay, and so one thing it's almost like step zero after you've started with a sketch is when you've read a problem or you have an engineering problem is to fully understand, do I have a closed system or an open system? That's the first thing that you need to understand why they're different. And I'm going to guess that you say, oh, I've got that already. That's great. Okay, then most of this video is going to be associated with statements of the first laws of thermodynamics. They're basically the same, but the first law of thermodynamics related to working with closed system problems and open system engineering problems. And I'm going to bet perhaps at this point you're thinking to yourself, how can I remember all of the formulas that are being thrown at me in this class? And so, in my opinion idea, what I want to suggest is that how can I remember all the formulas? It's not exactly the right question to ask. So I've X'd out on the slide, how can I remember all the formulas? And so perhaps you're saying, well, I'm going to depend on the formula sheet. I'm allowed to have a formula sheet in my class. Some classes are, some classes are not allowed to have formula sheets. But what I want to suggest is that you shouldn't use a formula sheet as a crutch without really learning what's going on with the fundamentals. And so in my world, I want to suggest to you that this is your best formula sheet. And I'll show you what my formula sheet looks like. My paper formula sheet is a blank sheet of paper because as I was going through the class as a student, and as a graduate student, then as a practicing engineer, there was no such thing as having formula sheets available when we were being tested on our performance in quiz, test, and exam situations. There was no such thing as a formula sheet for me in thermodynamics class. Okay, so step zero, after you've read a problem, tried to draw a sketch, you've got to decide, do I have a closed system? Here's my little example of a sketch. Do I have a closed system or do I have an open system? And so very quickly you say, well, this is second nature to me. The mass is fixed within a control surface for a closed system, but in an open system, we have mass flowing into and out of some control surface. So there's mass flow associated with it. There's a rate of which heat is added, a rate at which work is being done. And I hope that you're saying that you've got some familiarity with these dots. So you're seeing that there's something different about these sketches. Look, there's Q dot, and over here there's no dot. And here there's W dot over here in the closed system, no dot. And so a key to your success in this class is understanding the dots for an open system. And I'm going to try to talk more about that as we go along. And so the purpose of this video is I'm going to try to show you as best I can how to keep it simple. How do we keep this, the fundamentals simple? Because there are a good number of fundamentals that you're going to need to master to perform well in this class. I want to help you keep it simple. Okay, let's start out with a closed system. The first law of thermodynamics for a closed system, I've started with a sketch to show my good generic sketch of a closed system. Wow, how many piston and cylinder problems have we had so far in this class? A good many. And I'm going to go right back to your textbook to chapter 2, in which energy balance was discussed. And I've got a screenshot of good old equation 2.35b. That's a good fundamental starting point for the first law for a closed system. And just for talking, let's say we're going to analyze a process going from state 1 to state 2. And here's the screenshot. And I'm going to have to tell you that there's no way I could really memorize this formula in my head the way it's written. Well, let's look at the terms first. Delta KE, the change in kinetic energy. Delta PE, change in potential energy. Delta U, change in internal energy of the closed system, equals heat transfer in, capital Q, minus the work done by the system, W out. Okay, I got to tell you that for some way, when I'm learning things, there's no way I can memorize that. I want to show you the way I got this equation 235 into my head. Okay, here's my sketch again. Okay, and here's the way I was taught. So I had some terrific thermodynamics instructors, and they guided me through this. I didn't figure this out on my own. But on the left-hand side of the first law equation, what we did was I write down the energy transfer terms that are occurring at the system boundary. Notice how heat transfer and work, they're crossing the system boundary. They're forms of energy crossing the system boundary. I write those on the left-hand side of the equation. Q in minus W out equals the energy change terms on the right-hand side of the equation. Delta U plus delta KE, delta PE, and delta other energies, things like surface tension energy, magnetic energy, that we don't cover hardly at all in this class. Okay, so do you see how here's the screenshot of the textbook equation. I'm going to have to tell you that at least for me, and moving through the class and getting better at problem solving, this enabled me to get this first law for a closed system in my head without needing to depend on a formula sheet. Q in minus W out, those are the energy transfer terms at the boundary, equals the change in energy of the closed system terms. Okay, and some details next. All right, so this fundamental that I've circled in red, that's what I have in my head. The next thing is in problem solving, this delta U. Well, what's that all about? Well, delta U is going to be U for process 1 to 2. It's going to be capital U2 minus capital U1. And then I let the other, because most of the time in thermo class, I'm dealing with internal energy changes for a closed system. And numerically, I'm not working with a lot of problems that have changes in kinetic energy or changes in potential energy, so I don't worry about them quite so much. But I have the ability to go back. right? What do I do next? The next thing I do when I'm problem solving is recognize I'm looking, in many cases, I'm looking up internal energy changes in the back of the book, and those are specific internal energy, kind of like BTUs per pound mass or kilojoules per kilogram. And so I remember in my head quickly that I can change capital U2 minus capital U1 down to M times little u2 minus little u1. And if I'm faced with kinetic energy changes or potential energy changes, I can quickly recall how to get something actionable rather than delta KE or delta PE. And remember over here, potential energy, this Z term, that's not the compressibility of a gas. Z is a vertical height above a datum, above like the ground. So that's what this Z term, change in Z term is here for potential energy. All right, so it's easy for me to remember. I've got this in my head. I've got the fundamental in my head. And then quickly, I can, on a piece of paper, pencil and paper, I can write down what I need to solve a problem. Right. A lot of times in the textbook and given homework problems, you're asked to find little q in or little q out. You say, well, what does that mean? Yet another formula. I'd better put that on my formula sheet. That's not a good approach. Okay. If you've got this fundamental in your head, quickly you can remember, you can get down to this step and then divide both sides by M, the mass of the closed system, to get little q in minus little q out. That's Q over M, W over M, okay, equals the change in little internal energy, the change in little KE, the change in little PE. And so what I've done in this slide is try to show you, okay, here's your head. You've got this sort of in the formula sheet in your head, and you can generate the others depending on the problem you have. I hope this is helping getting your wheels turning on how can I simplify what's going on in my head so I don't have to depend on a formula sheet. Okay, that's the closed system. First law for a closed system. We're done. Now let's talk about the first law for an open system, any open system. And so here is my generic sketch of any open system. It's a cloud. I have multiple masses flowing in, multiple masses flowing out. I've got heat transfer coming in at some rate across system boundary, some output power work at a certain rate passing across the system boundary. That's my general setup for my open system. I'm going to go to my textbook, chapter 4. So I hope that everybody's getting into and working through chapter 4, which is open systems. Okay. And you write down and this, let's see, equation 415, good old equation 415 is a general statement. It's the fundamental statement of the first law of thermodynamics for any open system. Very powerful. But I'm going to have to tell you that there's no way I can get this equation 415 in my head. No matter how hard I try, I just can't get it in my head in the way it's written. So I'm going to try to show you how I can get this fundamental statement of the first law of thermodynamics, equation 415. How can I get this into my head? Okay, step 1, understand the dots. Understand the dots. Notice here, this looks similar to the first law for a closed system, but it's more complex. And also these dots are starting to appear. What do these dots mean? Well, in general, the dots represent some type of rate. Dots represent rates of variables or properties or things like that. And so in general, I've got question mark dot equals, well, the time rate of question mark. So think of a dot over top of a variable as a rate. Okay, so this is heat transfer rate, work rate, also known as power. And M dot, that's mass flow rate. Mass flow rate, M dot, mass flow rate. That's a fundamental. You got to get that in your head. No formula sheet's going to save you if you can't get that in your head. All right. Next is let's understand the basic variables of this equation 415, fundamental statement, first law, open systems, dE dt. More on this in a second, but do you see that it is a rate, d by dt? It's a rate of change of something. All right. Q dot, the rate of heat transfer into the system. That's going to be like BTUs per second or kilojoules per second. Oh, kilojoules per second, kilowatts. W dot, same type of idea, except it's the rate of doing work out. Okay. Units, BTUs per second or kilojoules per second. That's a kilowatt or horsepower. M dots, these are mass flow rates. H, this is the property enthalpy, the specific, intensive property enthalpy, intensive property enthalpy, BTUs per pound or kilojoules per kilogram. And then finally, a kinetic energy term and a potential energy term. You're starting to see that similarity that you're already familiar with. Understand the terms. Next thing. Understand this I and E business. Understand what I means and E means. So let's see, I. Think of I as in, starts with I, or entering. Okay, that's what I stand, that's what these subscripts I stand for. E, well, that would stand for exiting. Think of E as exiting or out. I think of it as exiting. E, exiting. I, in. Next thing, the left-hand side of the first law, statement of first law, open system. Okay. dE dt of the control volume. That's the way you say that. dE dt of the control volume. It's the rate at which the energy contained within the system, control volume, is changing. The open units, kilojoules per second, or BTUs per second, or foot-pounds force per second. Those to keep your units straight throughout. Okay, and so think of an open system, that cloud, okay, gaining or losing energy as time goes by. In other words, you could maybe think of the cloud as getting bigger, more energy in it, or smaller, losing energy, or getting hotter, gaining energy, or getting colder, losing energy as time goes by. Next thing, understand the sum signs. Notice here, summation of all the entering things. It's a glob of stuff. The sum, you've got to account for and add up all the exiting things, terms. Okay. And here's my sketch. And so on the sketch, recognize that I, visually, you got to account for all these things going in. And E, that means you've got to account for all the things going out. Okay. All right. So understand I and E. What does all that mean? Okay. 6, understand how to simplify the general statement of the first law for an open system. So real quickly, let's do some example problems quickly. How would this statement of the first law right out of your textbook change if you had steady flow? In other words, things aren't changing in time. Steady state, steady flow. All the inflows, they're all kind of the same. When you're looking at your watch, they're not changing in time. Outflows, not changing in time. So do you see that this left-hand side would become 0? The rate of change of energy contained in the control volume, the rate of change of anything of question mark with respect to time for steady state, steady flow situations is 0. So the left-hand side would become 0 for steady state, steady flow. Another example, what if you got one inlet and one outlet, only one thing going in and one flow going out, one flow in, one flow out? You see that that you're going to lose these summations, right? You only got one thing in and one thing out. How about an example of no change in kinetic energy? Well, that's pretty easy. I would just strike out these terms. and no change in potential energy, same idea. I'd strike out the potential energy terms. So I think you get the idea of how, depending on my problem, how would I simplify this fundamental relationship? Now, I'm going to have to tell you that there is no way that myself personally can memorize. I was not able to memorize this formula, this fundamental, the way it was stated. So I'm going to try to show you the way I was able to get it into my head for problem-solving situations. Okay. First thing to do, let's a special example of steady state, steady flow situations. Steady state, steady flow. Things aren't changing with time. I hope I convinced you to see that for steady state, steady flow situations, the left-hand side of the first law becomes zero. Okay. And so in your mind, you can, what does steady state, steady flow mean? It means that when you're looking at a piece of equipment and you're looking at it at breakfast time, it's doing exactly the same thing at lunchtime. Things are not changing with time. Steady operation. All right. So let's what I want to do is take you through flipping the textbook equation around, recognizing that for steady state, steady flow, that the left-hand side of the starting point screenshot is zero. The left-hand side, zero. I want to show you the way I'm able to get this statement of the first law in my head for steady state, steady flow situations. The first thing I want to do is I want to separate my Q dot and W dot. In other words, my boundary phenomena, what's going on across the system boundary. I want to get that isolated from the other terms. And so at first step, I'm just going to keep those on the right-hand side. And then what I want to do is take these big terms and flip them to the left side over there with zero. Okay. And so do you see that on the left side over here, I've got all these exiting terms minus the entering terms, into, in. Okay. That's kind of on the left-hand side. And on the right-hand side, I'm left with Q dot minus W dot. Now, the next thing I do is I simply flip the left and the right-hand side because I like, in my head, I can keep these energy transfer rate terms straight for some reason if I've got them on the left-hand side. Okay. So I've got Q dot in minus W dot out on the left side, energy balance equals the other energy change terms. So I've got the sum of the M dot exiting, H exiting, kinetic energy, potential energy exiting. So that's a big block there, minus what's coming in, the sum of the M dot in, enthalpy in, kinetic energy, and potential energy in. Okay. And so in the big picture, I've got left-hand side, Q dot in minus W dot out, energy transfer rate terms at the system boundary equals, right-hand side, energy change terms for mass entering and out of, in and in on the right, out, left, into and out of the open system. And so my suggestion is this worked for me. So consider thinking about changing your viewpoint around a little bit. First law, left-hand side, terms that involve energy crossing the system boundary. Right-hand side, terms that involve energy transfer, okay, into and out of. Remember, we've got steady state, and so the closed system is neither getting bigger or smaller. It's neither gaining or losing energy. This is steady state, steady flow, like I have in my yellow text box. Okay. Now let's go another step further of simplification. Not only will we have, let's look at the situation where we have one inlet and one outlet. So notice how my sketch has changed. I've only got one thing going in at M dot and one thing coming out, M dot. Well, look, if I've got steady state, steady flow and one inlet and one outlet, the mass flow going in must exactly equal the mass flow going out. I've really got a simple simplification there. that's going to pay off. I've written down sort of the rearranged screenshot from the textbook for steady state, steady flow. Left-hand side, Qn minus W, Q dot in minus W dot out. Right-hand side, the sum of the M dot leaving, H leaving, minus the sum of the M dot in, H in, and those other terms. That's the starting point. How will I simplify? I will simplify by, let me go back a slide. Remember here, M dot out equals M dot in. So I can pull that M dot out of both terms and group the two terms together. So I've got left-hand side, same, Q dot in minus W dot out equals M dot times bracket M dot. There's only one single M dot. And then I'm going to group together my enthalpy change terms, my kinetic energy change terms, and my potential energy change terms. I can get that in my head. I don't know about you, but I can get that in my head. I've got it in my head, and I used it for years for steady state, steady flow, one inlet, one outlet. Didn't need to depend on a formula sheet. Now, in homework problems, in the textbook, in many examples in the textbook, in many homework problems, the textbook divides this fundamental both sides by M dot. And let's see what and so you don't have to have this in your head, okay? But you have to be able to get to it quickly. Q dot in divided by M dot, well, that's just little q in. Same W dot out divided by M dot. That's just little W out. And on the right-hand side, it really makes life pretty easy, simpler. Enthalpy change, H2 minus H1, out minus in. Kinetic energy change term, out minus in. And potential energy change term, out minus in. So this lower expression is commonly used in your textbook and for homework problems. Okay, so I've repeated this to make a little note here to you. You won't believe how frequently this model, first law, steady state, steady flow, one inlet, one outlet, you won't believe how frequently this is used throughout the rest of the class and further in engineering practice, subsequent classes that you're going to be taking in mechanical engineering. You won't believe how much repetition there is in this statement of the first law, steady state, steady flow, one inlet, one outlet. And that's why I've got the little icon of your head associated with this fundamental. It's more than just a formula. Okay, now this section is going to be for problems that are encountered not very frequently, very infrequent, but you do need to have enough understanding to be able to get through this part. There are a couple of homework problems that you will be assigned, and it's possible that you'll have this type of problem on a quiz or on a test, but it will not be frequent. First law of thermodynamics for an open system undergoing a transient process, and I've called it USUF. That's not a word. It's just an acronym, USUF. That means uniform state, uniform flow, not steady state, steady flow, uniform state, uniform flow. I'm going to give you an example of this in a second. And so here's what that means. The inflow and or outflow rate is a constant value during a process, during a filling process or a draining process, but it occurs over a specific period of time, not continuously. So this type of transient process is associated with filling something up or draining something, okay, from time equal 1 to time equal 2. Let me give you two very typical examples of uniform state, uniform flow, transient processes. These would be indicative of the type of homework problems you're going to get as an undergraduate and also early graduate student. So one basic example is filling a vessel. Wow, so I've drawn a piston and cylinder. How is the piston and cylinder an open system? How is that an open system? Well, that's because I've got this piston and cylinder, but I've got mass, I've got some flow coming into this piston and cylinder, I'm adding mass at I, in. And I start filling this vessel at state 1, and I quit filling the vessel at state 2. It's not continuous, okay? And during that process, heat is added and or work is done. So that's an example of a transient process of filling a vessel from a starting point to an ending point. The other basic type is draining a vessel, or a vessel that's leaking. It's got a leak in it, a pinhole leak in it, perhaps. Okay, same sketch. I'm showing a piston and cylinder. Okay, heat in, work out. Wow, looks like a closed system, but no, I've got mass transfer because perhaps there's a leak in this tank. I'm losing mass at a certain known flow rate, for example. In other words, I have mass leaving at state E, but I start at some known state 1 and end at some state 2. So these are examples of uniform state, uniform flow, transient processes. It's going to be very unusual, not very frequent that you have problems like this. So I want to recommend that you don't just depend on this crash course. Go to section 412 in your textbook, transient analysis. And the textbook does a great job of explaining continuity equation, conservation of mass. Here we go, mass balance, and the energy balance, the first law of thermodynamics for uniform state, uniform flow. Okay, and here's a screenshot of equation 425, and I want to show you I want to flip it around. I want to use sort of my same approach of flipping it around so that it's a little more understandable on how to approach a problem that's transient, uniform state, uniform flow. Here's the screenshot of the textbook, equation 425. And so what I want to do is flip this around. So remember, I like having the left-hand side being the energy transfer phenomena across the system boundary. So I've got Q in minus W out on the left-hand side of my equation. All right. So therefore, I've got, okay, so you can kind of think about moving this around left. However, on the right, so this will sort of become the right-hand side of the equation. This is capital U2 minus capital U1. The total internal energy at the ending state minus the internal energy of the system at the beginning state. Okay. Now, I've got to flip these terms around over to the other side. And so do you see if I'm going to flip that over here, I'm going to have a plus sum of the m dot leaving, h leaving, I said m dot, mass, the mass that left during the process times the enthalpy leaving minus m, not m dot, the mass that entered, that came into the open system during the process times the enthalpy that came in during the process. And so do you see that these are identical mathematical equations, but I'm going to have to tell you that it's easier for me to visualize what's going on in my head if I formulate equation 425 in this manner. And then finally, well, I have to split out, well, what is capital U2? Well, it's simply the mass at state 2 times the little internal energy, the intensive kilojoules per kilogram U2 at state 2. Same idea. If capital U1 is simply M1 U1. And now I've got things, notice here on my right-hand side, I've got all my properties in the intensive property form, kilojoules per kilogram or BTUs per pound mass. Okay. And I got to tell you, this is a little easier for me to visualize. Now, let's see. An admission. Even with this simplification, I'm going to have to tell you that I do not have this fundamental in my head. Whenever I have a homework problem or even a practical, when I'm working for a living and I've got a problem that is like this, I have to go back and refresh my memory, go back to the textbook, back to my own notes, and bring this back out as I'm solving a problem. So I'm going to openly admit that I do not have this uniform state, uniform flow, transient first law in my head. So shame on me, but in my experience, I haven't done enough of these problems frequently enough to get it into my head. Okay, let's dissect the terms in this statement of the first law: open system, transient process, uniform state, uniform flow. Left-hand side, heat added to the control volume during the process, work done by the process. Okay. M2U2, internal change at the end of the process, M times little u. Internal energy at the beginning of the process. The sum of the M leaving, H leaving, the sum of all the mass flows times the enthalpies that have left during the process. And then finally, the sum of all the mass flows out times enthalpy out, entering. This is where I have my mental lapses, by the way, and I have to come back and review my notes. Okay, because in my head, I cannot fully recall without help in reviewing notes, which goes first, I or E. All right, so understand all the variables in this expression of first law, transient process, uniform state, uniform flow, kind of like filling a vessel or draining a vessel. Okay, we're coming down the home stretch, finish line. So we're summarizing. Okay. So what I want you to do is think in your head, compare the first law of thermodynamics for a closed system and an open system. First step of any problem solving, do I have a closed system or an open system? If I have a closed system, do I have this in my head? Q in minus work out, boundary phenomena, left-hand side, equals change in internal energy, M times little u. Kinetic energy, change in velocities, change in potential energy, change in vertical height. Now, how does that compare to an open system? Well, let's not go through all the generalities. Let's say we've got an open system. We have steady state, steady flow. Only one inlet and one outlet. It's a special situation, but it's a very frequent situation. One inlet, one outlet, steady flow. Left-hand side, boundary phenomena. It's not Q in and W out. It's Q dot in, W dot out. Rates of energy transfer equals one M dot, one in, one out. M dot in equals M dot out. So I've collected my term, and I've got a bracket of terms. An enthalpy change term, not internal energy, enthalpy change term, kinetic energy change term, and potential energy change term. Do you see how similar that is? Do you see how you can get that in your head without depending on a formula sheet? This has saved my bacon over and over again, and it helps speed my performance when my time is limited, like a quiz or a test, or when I have to do something in my day job, and my supervisor says in the morning, I need you to analyze a pump, and I need the answer by lunchtime. I got to get moving. One last reminder. Specific work and specific heat transfer that occurs so frequently in your textbook and confuses so many students. So look, it's a simple slide, but I want to help you get this in your head. If you have a closed system and you're asked for little W out, kilojoules per kilogram, or little Q in, kilojoules per kilogram, well, that's simply capital W out, the work done, divided by the mass of the closed system. Heat transfer in divided by the mass of the flow system. And a number of students, they said, okay, I got that. And then we get over to problems with open systems, steady state, steady flow, one inlet, one outlet, where we've got a single m dot, a single m dot, single mass flow rate, we can formulate a little w out, which is defined different. Notice how it's different. Look at it with your eyes. You've got w dot divided by m dot. And so let's see, w dot out, that's going to be kilowatts, but that's a kilojoule per second, isn't it? Kilowatt, kilojoule per second. M dot, kilograms per second. So you think about units, that's kilojoules per kilogram. Same units over here as a closed system. And of course, the same idea for little qn. That confounds many, many students because the units are the same between open and closed system, but different way to define little w out and little qn. So that's really important. Recognize that little w out for an open system, steady state, steady flow, one inlet, one outlet, is w dot divided by m dot. So many homework problems for open systems ask for kilojoules per kilogram. That's what this is all about. Okay, so our final recap. Can you use your eyes and your head to simplify what you need to commit to memory? I call that learning. That's learning and not depending on formulas on your formula sheet. Can you develop some tricks for yourself for keeping things simple enough so you can keep things in your head? That'll work for you. Now, these are ideas for you to think about. I want you to find out what works for you. What works for you? Pure memorization of formulas, that did not work for me. Maybe it'll work for you. So just recognize that I'm trying to throw out some ideas to try to get your wheels turning so you can simplify this. Lots and lots of formulas that are thrown at you, but recognize they're more than formulas. If you can really seize on the fundamentals, that's going to pay off for you in the long run. So that's it. I hope that these slides and my little discussion has helped give you some ideas on how do I get that formula sheet, the fundamentals of the formula sheet in my head so I don't have to be depending on a formula sheet. If you're allowed to use a formula sheet, great, use it, but also recognize there's some really neat tricks to help you get things into your head, to learn things rather than purely depending on formulas that you're scratching down on an ever-growing and font size decreasing formula sheet. Hope that helps. Hope to see you again sometime soon.